Okay, good morning. Okay, shall we start? ザフラさん、you start first? I cannot hear your voice. うーんと
Can you hear me? Hello?
Your voice is
Small?
small.
ごめんください。Then,
Now it looks okay.
okay?
Yeah, okay.
Okay. So, based on discussion yesterday,
うん。
first we have to determine the demand of capacity of the damper in the coupling beam. So we can do this by steel beam in the stereotheory analysis. And then before we design the hybrid damper, first we have to know the properties of the damper itself. So from the lab, we can test the viscoelastic material with the friction damper. And from the properties that we get from the lab test, then we can apply for the damper design, and we can apply in StereoTD. And then we can do the dynamic analysis, and then we can check with the displacement-based design method and double check with the time history analysis. And this is the first concept that we can try. So I removed the middle bolt at the viscoelastic damper.
うん。
And then if we need to increase the capacity of the damper, we can do double slice like this, or we can put one at the bottom, one on the top, like a two damper.
うん。
And then I try to analyze some properties inside StereoTD with 18 story. So this one 300 and 300, it looks it can dissipate a lot of energy. And this one, if I reduce the friction damper to 170, so it reduces the displacement, but it can reduce the force, but I think it dissipates less energy. And if I change to 200, 200, so this is 200 by 200, it looks like this. And I try to check some result. So with El Centro and Kobe, so the blue color is a steel beam. So
How did you decide friction force?
friction force we can calculate by the number of bolts.
Number? No. In the previous slide,
This one.
this is Mateo, is this a friction? Okay.
Yeah,
How did you decide FY?
Fy is the maximum force from the fuse.
Yeah, but what is the reason of this number?
It depends on the number of bolts. So for example, okay.
Number of bolts.
So first we have to determine the force in the steel beam. For example, here I use steel beam, and then we can see what is the maximum force. So it's around 200. Here we can see 200. So I decide to design less than around this value, but less than the maximum value of this serial damper. So I took 200, and so the maximum here is based on the friction damper. So if I want to limit the damper as 200 kilonewton, I can set here the friction damper as 200 kilonewton.
Well, I think you should first analyze only viscoelastic.
Only viscoelastic?
Yeah.
Okay.
Then you can find how much shear force in the beam.
Okay.
Then you want to reduce. I mean, you want to limit the shear force less than, I mean, the maximum shear force of the viscoelastic damper.
Maybe we also can do the lambda parameters and say like 1 and then 0.8, 0.6, and 0.
Yeah.
Okay. I can try that.
Mm-hmm.
And here I So by using the hybrid damper, we can reduce the force. So and then also this is the ductility, the beam ductility will be higher compared to the steel beam. And here, I just want to highlight this one. So if we, for example, the damper with the building with the damper, because it can have more displacement. Actually, the building displays more into the maximum displacement that we set in the damper. For example, 4 centimeter. It's much more bigger compared to the steel beam, but it can reduce the accelerations.
Mm. 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 Why steel beam is so small displacement?
Displacement. I believe because it's rigid, it doesn't displace a lot compared to the hybrid damper.
How much ductility factor for steel beam?
Steel beam. Here.
So it's not yielding.
It's not yielding. Yes, it's not yielding, Sensei.
So steel beam is so strong.
Yes. I actually for the steel beam I used the 600 by 300. Maybe it's still strong for this model.
How did you select this size?
The size, it is a trial. I didn't change in the Stereo 3D when, for example, so this is
So it's a reinforced.
no, it's this one.
So why did you select this size?
Uh, I know this size is about 300. The capacity is around 300 kilonewton for the shear capacity. So it's bigger than the, and it doesn't yield. It reduces. I try.
It's yielding by shear.
Yeah,
Really? No. Could you check steel beam again?
still there.
You assume some shear damper? Non-linear.
I should. This one, not
Yeah,
that.
you must do no damper first.
Okay.
Why beam is yielding in shear,
Shear and also flexure.
but there is no damper. Something wrong. Could you select one beam? I want to see hysteresis.
Okay.
Okay, seventh floor. Okay. Hmm. Oh yeah, it's start yielding 1.2. Mm. 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 Yeah, we must make some story. So steel damper looks good. I mean, it's yielding, but the deformation of the building is very small. And I think it satisfies the design criteria, right?
Yes.
So, so how to say? The story is the original building is not good.
Okay.
Then we must put damper to improve.
Okay.
Yeah. But in this case, original building is good already.
Okay.
So people may ask why you must put damper. So we must, how to say, what to do? No.
We know last time we checked from the Harris sample. We can try to because Harris only use concrete beam and steel beam, and then we can try to see if we can improvise the performance of the structure based on Harris model.
No. We must design by ourselves, not to follow Harris example.
But we have to like, how can I say, to have a reference based on.
Well, we can start to reduce size of beam gradually, and how to say, for example, in this case, ductility factor is around 3. So it's not bad. But if you reduce the size of beam, probably ductility factor will be much larger, more than 3 or why beam ductility is very small in case of steel beam here?
I'm so not sure. I will check again.
Yeah, this is around 3 ductility factor. So yeah, so maybe please check again. Maybe this building is okay.
Okay. Okay.
Please check.
Seriously, I have one question. Like last time, I tried to put push hole dynamic this one. Sorry, load distribution put in the building. So I already put this distribution based on Paris. But when I run, it doesn't show any result. Like it's static here. I don't know why. It's
Oh, okay. Could you do it again? What kind of file did you?
load distribution.
Load
So
distribution.
this was static.
Static.
And
what?
Input this one.
And this is a load distribution.
Text file, right?
Yeah. Okay, and could you open?
Open.
Then.
Okay.
Yeah.
And then
Analyze.
Force, right? And then yeah. it doesn't show result. But dynamic analysis and static is okay. Only the
Maybe load is so small.
look is so small.
Yeah. How did you?
I think it's in kilonewton.
No. Maybe you made a mistake. Could you
Okay.
open Stella again? Could
Okay.
you show me Stella again?
Stella.
Yeah. So you could you select the distribution, not the force?
Distribution.
Yeah, and
This.
no.
Oh, this
Not
one.
AI. Yeah, original.
This
User defined.
user
That one.
defined
Yeah.
force.
And
And
not force.
then,
You must put the target. Yeah.
oh, like for example, this one.
Yeah, for example, yeah. So you push the building,
Uh-huh.
using the distribution you defined.
I see. Okay. Thank you, Sensei.
So it's working, yeah.
Okay. Thank you. That's all for today's lesson.
How is the Python code? Do you think you can do it?
I try to learn. I still try to do it, but I also ask ChatGPT.
There are many students who already know Python. Maybe you can ask
Yes,
help.
I can ask Gao-san.
Okay, yeah.
Okay, Sensei.
So who is next? Ataya-san?
Hi, Sensei. May I share the screen, Sensei?
Yeah. You must prepare for the preliminary, defense. Yeah, okay.
Okay, Sensei, I will. Before that, Sensei, I used the wind load on the 25 story model that I showed in the last meeting. This is the wind load time history that is obtained by this formula, Bernoulli formula. Then I applied this in Estera, and this is the maximum displacement results without TMD, with single TMD to turn to the fundamental period. And these 3 hours turn to the two nonlinear area of the capacity, pushover capacity curve. And this is multiple TMD, which is 3 TMD turned to each of these time periods.
What is the meaning nonlinear?
It is just a name, Sensei, because in pushover capacity curve, there is a segment in the origin, close to the origin is linear part. After that, the nonlinear of the building starts when it starts yielding. Maybe I can show it in the For example, here, Sensei, from O to A, it is linear, elastic.
So you mean
there's 3 segments, Sensei.
How do you decide the stiffness of tuned mass damper? So you decide the stiffness of tuned mass damper from this slope. Stiffness.
First, the stiffness of the building, Sensei, according to each behavior of this.
Okay.
Then from the period of the building, we have some formulas and can find the stiffness of.
Okay. So in case of wind load, building will be elastic range. So I don't know.
Since it is, for example, in here it is about 700, but with this wind force, of course, the Bashir will go beyond the 700. It will be larger, so it will.
Really? Oh. Okay.
So this is the displacement, and this is the 25th story acceleration, and these are the peaks. Peaks are very similar.
Without TMD, with quantity. Okay.
Fundamental T, Sensei. The first nonlinear segment.
Yeah.
And the second nonlinear segment, but multiple TMD. It shows multiple TMD reduce the maximum acceleration more than other cases.
Okay.
And that's all, Sensei.
Okay. So, did you start writing master thesis?
Yes, Sensei.
Can I see, the draft?
Actually, Sensei, we have a meeting, individual meeting next week on Monday, on Tuesday.
Okay. So,
yeah.
You want to show at that time? Okay.
Yes. Thank you.
Okay, so Ahmed-san, do you have anything you can show me? Your mic is mute. Could you? Okay.
Yes, Sensei.
Yeah. Fine. Now.
Can I share my screen? Can you see my screen, Sensei?
Yeah.
Okay. This is the progress of my work relative to the big flow chart of my work. I did some modifications to the flow chart. First, I started the first step. I started to do the analysis for the couple shear wall without using dampers. And the first issue of my first analysis is to get the effective damping ratio and to get the effective performance point and to get the yield point. So first I tried to do that using the capacity spectrum method, which is mentioned in the ATC40, to get the effective viscous damping and to get the performance and yield point, and again to calculate the ductility and dissipated energy. But these 2 points are still under investigation because there are many methods discussing how to get the performance point, which one is more accurate than the other one. Then I'll try to do the same process, but after designing and adding the dampers to the system. So this is the system. I just assume the wall length, the wall thickness. The only variable parameter for now is the height of the building, 5, 8, and 11 story. Later, maybe I can add other variables like the wall thickness, dampers, and without dampers after designing if we need dampers, of course. So then, this is a summary for the methods to calculate the performance point for that system. There are 3 main methods: the equivalent linearization approach, and the displacement modification, and the nonlinear time history analysis for the equivalent single degree of freedom. For me, I started with the capacity spectrum method using ATC40, which represented in the graph to get the performance point and the yield point. Then I think I'll try to spend more time in this step just to use another ways and to compare between the results between these ways. I was thinking to get the equivalent single degree of freedom system, do cyclic pushover analysis, and to get the effective damping of the system. Maybe I'll spend a little bit time in this step. So later. This is a summary for the design steps to get the steps to get the performance point and effective damping using the ATC40, the capacity spectrum method, to just estimate the initial stiffness, then to get the line another line 2, which represent the effective stiffness, and get the intersection and so on. This procedure is procedure C in the ATC40. There are many procedures in ATC40, and we will do many iterations. First, we will assume that the intersection between the elastic spectrum and the capacity curve is the performance point. Then we will go on from the first assumption until with many iterations until the ratio between the last and previous iteration is within this 5%. Then we can calculate the effective damping of the system, of course, with the original viscous damping, which is 5%. So we can get the reduction factors to get the modified response spectrum or the demand response spectrum. So this is my values. First, I started with the 11 stories building. I got the P effective for the first building, first system. Second, 8 stories, which is I get the P effective and the reduction factors. The 5 stories building, I got the the effective damping, viscous damping, and the reduction factors. Then I represented this on a graph. Just the first one is for the 11 stories couple shear wall system. We can see the performance point. We can see the reduced elastic spectrum. I did 3 iterations.
So how did you get this elastic spectrum? It is from Japanese code or?
No. It depends on the method in the ATC40. This method. I followed
this
this
is the
method.
American spectrum.
Yes, the capacity spectrum method. Yeah.
Okay.
So I got the performance point for each 11 story, 8 story, and the yield displacement. So I presented this on a graph. We can see without doing more iterations, the difference between the elastic response spectrum become smaller and smaller until we get the intersection with the pushover curve. And this is the displacement performance point.
Okay.
I also did the same for the 5 stories building. I also presented the ductility factor for each cable shear wall system, the performance point, and the corresponding shear wall ratio for each corresponding point for each wall. Actually, I will do the same process again, but after adding the dampers to the walls. First, we need to check if the walls exceed the yield point or not, but using many other methods. Because I just want to check this method again, the ATC40 capacity spectrum method.
Why ductility factor is so large? 29 is very large.
Yes, 29 is so large. Ductility factor is the ratio between the ultimate displacement and the yield displacement. And the yield displacement for the 5-story cable shear wall system, is very low.
How did you decide yield displacement?
I decide the yield displacement from this way. So. I get the yield displacement from the performance point using this method here. After getting the performance point, the yield displacement is the intersection between the initial stiffness line, and the horizontal line from the performance point using the capacity spectrum. So from this Excel first. So first I get the performance point, then I can calculate the yield point.
So for example, in this 11-story coupled system, how much yield displacement?
The yield displacement for the 11-story.
Yeah.
And the performance is 9.7.
9.7, and the dy is yielding.
The yield.
So if you divide the ductility factor is around 3.
But the performance, this is not the maximum. I mean, I get the factor from the maximum. I mean, the ultimate one, the ultimate displacement.
So how do you get the ultimate?
I get the ultimate point from the highest point on the pushover curve.
For example, you can extend any. If you push more, ultimate point will be more. How did you?
I tried this, but I tried to do this one, but it was in the same range. I tried to push more, but it was it increased, but not with a big percentage.
I don't understand.
Okay, for me, I can see that fertility factor is very high, but maybe I can check this again.
Yeah. Please think about the definition. Okay. Usually we divide. I mean, maximum displacement. In this case, a performance point is the
performance point.
Okay. And divided by yield displacement. Yeah. Maybe.
Okay. So then I calculated the absorbed energy, but I calculate the absorbed energy until the yield point, only to the yield point. I get the actual area under the pushover curve. We can see which is 3,000, 7,000, and 9,000 for each building. But this up to the yield point only. Then I checked using the time history analysis. I applied two time histories and matched it with the demand spectrum. The demand spectrum for the 8 and 11 stories almost the same. So I did just one matching process for approximation. And this is the result from the time history analysis. And I compared it with the results from the ATC40 using capacity spectrum method. We can see the time history analysis shows high performance point relative to the capacity spectrum method using ATC40. But later I want to spend more time with this to get the effective displacement. I want to apply many other methods just to do a comparison study between them. Then after this, just you decide to add either to add dampers or not. And this the design. I summarize the design steps for the viscoelastic with the friction device, which is viscoplastic damper, according to the paper. Maybe I just can skip this part. I think we discussed this later. This is the design steps for the viscoplastic damper. I'll go on with these steps, but later. and this I created the Python code.
Oh, good.
Yes, I created it yesterday, but I didn't revise it. I created the code for 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 many amplitudes and for an array of time from 0 with step 0.001. Yes. First, I define the parameters, the KD, which is for the KD was for the single spring, K and C with the parameters for the friction device. W omega, sorry, is the 3.14. Omega was 2 pi frequency. Frequency was 0.5, so omega was 3.14. I defined it as a constant, and the time step is 0.001.
Yeah.
Then I define the range, an array from 0 with step 0.01 and the values of amplitude. I also apply the equations. Then first to get the results, I have to get the UC, the displacement in the friction device.
Yeah.
Then to get the total displacement, last to get the force in the friction device, which equals to the force in the system. Then I have plotted a graph between the force and time for many amplitudes. Yeah.
Oh, you success to make it.
Yes, I did it yesterday. I did the main code. Then I asked the assistant to, I mean the online assistant in Anaconda to find the errors. He do better recommendations for me related to the array and things like that. And I applied this recommendation and run the code again.
Oh. Zafira-san, could you talk with Ahmed-san? He success to make a Python code.
Okay, Sensei.
And Ahmed-san, so also Python is new for you.
I used it for 2 or 3 times before, so I have a small experience with Python.
But yeah, I think your code is very good. Yeah. So, and how to say? So Zafira-san,
Yes,
for example, you must understand first 2 line import. Okay. So it's a kind of a library. You must use library for numerical analysis, maybe NumPy, first one. The second one is a library to plot, figures. Okay. And also there are some Python, how to say, function, NP arrange to make some kind of array. So Ahmed-san knows about this. And also, if you run Python, these functions will be kind of basic functions.
Yeah, I tried yesterday to Sensei.
Yeah. Well, anyway, you can use the same code.
But this one is only wave. We should find the force and displacement graph, right, Sensei?
Yeah. I want to see hysteresis also.
Yeah.
Yeah, this was for.
So there's another Python code for making hysteresis.
Okay, but yeah, almost. Okay. Good. And Ahmed-san,
Yes.
I think next week we will have a lecture of seismic design of structure. My lecture on
Wednesday. Yeah.
And I will explain capacity spectral method.
Yes.
And it is almost the same as ATC40. But I think this lecture will be very helpful for you.
Okay, Sensei. Yes, sure.
And let's see.
I have one question for
Yeah.
Ahmed. Did you ever try Stera 3D yet?
For what?
For analyze reading, because I think you use different software for
No,
this one.
for my analysis, I use this analysis I use Stereo 3D.
Yeah, I think capacity spectrum, obtained by pushover, right?
Yeah, by pushover using ASTCE.
Yeah.
The figure, can you go off? This one is the third slide. The third slide.
This?
Yeah. This
No,
is
this wall I created this wall just to create the visualization of the wall for the
okay.
for the analysis. I normally use the system, the Stereo 3D for the analysis.
Okay.
Okay. The data building, do you take from the paper?
For what?
For the properties. This properties is from the paper?
Wavelengths under.
No, it's just assumed. I
Assume.
created a first assumption just to compare between getting the performance point using ATC 40 and the nonlinear time history analysis.
Okay.
Okay. Ahmed-san, you know how to analyze building.
Yeah.
Good. Very good. Okay. Actually, let's one moment. Let's see. Okay, and no. One. Okay, so I asked to make a Python code for viscoelastic material here, this one. And then the next assignment is viscoplastic. Okay. So only the difference is after you calculate, for example, increment of damping, how to say? I will write down here. Okay. So first you calculate increment of dashpot displacement UC, and then calculate UC. Then next you will get the displacement of friction damper UK. So this part is different from previous one. So previous one, there's no step to calculate UK. Yeah. But in case of friction, damper, you need an increment of friction, damper UK. Then you must check this bilinear hysteresis, if it's over capacity or not, or it is going right side or left side. So the next step, I will prepare explanation, in this weekend, and I will send you. So maybe Ahmed-san, your next step is to write a Python code for bilinear hysteresis. It's a little bit, how to say, complicated, but not so difficult.
Okay, since I
okay.
try.
Yeah.
Okay.
Okay, good. Very good. So, let's see. Ataya-san, you must prepare for, yeah, we will have a meeting next week. And let's discuss next meeting. うーんと。うーん。うん。予備審査、仕事納め27、28、29。Next year? I am okay on Saturday, 23rd. Do you don't want to have a meeting on Saturday? Actually, other day I am a little bit busy next week.
Sensei, my suggestion, we can do next year, but if we have any update, we can just send you the result and slide to you. And if you want us to come to your room, we can come if you're free.
Okay.
Yeah.
Okay, so let's decide next year. Let's see. Okay, I am okay, 9.
I'm okay, Sensei.
4 or 5. I'm free.
I'm okay. I'm also okay.
Which day do you prefer?
5?
5? Okay. What time? 10 o'clock?
Okay, 10 o'clock is okay.
Ahmed-san, are you okay?
5, which day will be 5?
Friday.
Wednesday?
Friday.
Friday.
5
Okay.
of January.
Okay, Sensei.
Okay. So, Ataya-san also okay?
Yes, Sensei.
Okay. Ataya-san, under, Zafira-san,
Yes, Sensei.
after you attend JES symposium, and what will happen next step? I mean, you're supposed to write a full paper, no?
They doesn't give us any feedback. They just say thank you for joining the GESS. They doesn't say like please send full paper or anything.
Really?
Yeah.
I received the email from journal, and they propose free submission.
Okay.
And maybe Zafira-san and Ataya-san both submit paper. If we are lucky, we can submit for free for both paper.
Okay. Can try.
And this is one moment. So. So the journal is building. Let's see, under MDPI. So. Okay. Paper free submission invitation. Yeah, this one. Yeah. Okay, I will transmit this email to Zafira-san. There might be format of the paper.
Okay.
Okay, yeah.
Thank you, Sensei.
So, Okay, so if you anyway, I will send you some information about the viscoplastic damper.
Yes.
Shall we finish?
はい。
Okay, bye bye.
Bye.